All right, this is going to be our walkthrough for the homework assignment titled Integrals Test Review, just review for the upcoming test on integrals. So the first few questions here, we're going to be looking for a right, a left, a midpoint rectangular approximation, and the trapezoidal approximation. And the instructions say just find the right, left, and trapezoidal for like whether it's under or overestimate. But we're going to do it for the midpoint as well because they've added that in. In recent years, there's been a question or two about that on the AP test, so we'll do that as well. To start off with, we're going to do the left approximation, right? And we're going to approximate the area underneath the curve 2x squared minus 1 from 1 to 4, from 1 to 4 with 3 subintervals, right? And really, we're approximating the integral, not the actual area underneath the curve. Because we might, for some portions of these, not for this particular one, but we might have some sections below the x-axis. So we'll start with our left, which means we're going to use our left endpoints of our subintervals, and our subintervals are going to be from 1 to 2. I guess we'll put that into a bracket, actually. Might as well. So our subintervals are going to be 1 to 2, 2 to 3, and 3 to 4. We know they're each of length 1 because we're going from 1 to 4, right? 4 minus 1 is 3, and we have 3 subintervals, and thus each one has a length of 1. So this will apply for all of our different approximations. And as we do the left one, our left one ought to then be the length of the subinterval, 1, times the value of the function at 1, so 2 times 1 squared minus 1, plus then 1 times the value of the function at 2, which will be 2 times 2 squared minus 1, and then plus 1 times the value of the function at 3, which will be 2 times 3 squared minus 1. And that should be our approximation for our left approximation. So the first one here, we've got 1 times 2 minus 1, that's just 1. Then we've got 2 squared is 4 times 2 is 8. 8 minus 1 is 7, so 1 plus 7. And then we've got 3 squared is 9 times 2 is 18, minus 1 is 17. And so we have 1 plus 7 plus 17, which is 25. And then we need to determine if that's an under or an overestimate here. And so the way we'll do that is by determining if the function is increasing or decreasing. So we can do that by finding the derivative of our function, right? So f prime of x is equal to 4x, right? And so that we know that 4x is greater than 0 on the interval from 1 to 4, right? And therefore, the function is increasing. And if a function is increasing, then a left approximation will always be an underestimate, right? Because we'll be drawing those rectangles underneath. Right? And so our reasoning would be because the function is increasing on that interval. Then we'll do our right approximation. So our right approximation, we're just going to use the right endpoints of each of those intervals. So that'll be 2, 3, and 4. Well, we've already done this with 2, right? 1 times 2 times 2 squared minus 1. Minus 1 there. Plus 1 times 2 times 3 squared minus 1. And now we'll do 1 times 2 times 4 squared minus 1. And of course, the ones that we already did are going to have the same values, right? 7 and a 17. And then 4 squared is 16 times 2 is 32. And then 32 minus 1 should be 31. And so when we add those together, we end up getting 55. And this time, because the function is increasing a right approximation, the rectangles are going to go over. And so this is going to be an overestimate. And the reason being because the function is increasing on that interval. And I think for our midpoint and our trapezoidal, we'll just go to a new page for those. So our function again that we're looking at was to approximate the integral from 1 to 4 of 2x squared minus 1 dx. Right? And so our midpoints, if our intervals were from 1 to 2, from 2 to 3, and from 3 to 4, our midpoints are going to be 1.5, 2.5, and 3.5, or 3 halves, 5 halves, and 7 halves. So our midpoint approximation is going to look like 1 times 2 times 3 halves squared minus 1, and then 1 times 2 times 5 halves squared minus 1, and 1 times 2 times 7 halves squared minus 1. Okay. So that's going to be our midpoint approximation, just taking the midpoints and plugging them into each of these. So 3 halves squared is 9/4. If we multiply that by 2, that's 9 halves. And 9 halves minus 1 is 7 halves. So we got 7 halves plus, then we have 25/4 times 2 is 25 halves. So when we subtract 1 from that, that ought to be 23 halves. And then the next one would be 49/4 times 2 is 49 halves. Minus the 1 ought to be 47 halves. And if we add all of those together, 47 and 23 is 70, plus another 7 is 77/2. And we want to, again, figure out if this is an under or an overestimate. Well, for the midpoint and the trapezoidal approximation, that's all dependent on the second derivative, right? So we already had f prime was equal to 4x, so f double prime is equal to 4, which means that this function is always concave up, which we knew just by looking at the function, right? Because it's just a parabola with a value that is positive, right? And so when a function is concave up, a midpoint approximation is going to be an underestimate. That's just a rule. We need to know that rule. And then lastly, we're going to do our trapezoidal approximation. Since we have equal subintervals, we can just use our formula. Our formula says b minus a over n. So that's the endpoints of our integral, 4 and 1. 4 minus 1 divided by the number of subintervals, which is 3. So b minus a over n, or sometimes we call that h, over 2 times our first y value. Right? So that's just 2 times 1 squared minus 1. And then plus 2 of our second y value. So that's going to be 2 times 2 times 2 squared minus 1. And then 2 times the next one, that's going to be 2 times 2 times 3 squared minus 1. And then our last one, which is the one at 4, we just do 1 of. So this will just be 2 times 4 squared minus 1. And whatever that comes out to be should be our final trapezoidal approximation here. So I have 4 minus 1, which is 3. 3 over 3 is 1. 1 over 2 is a half out in front. So we have 1 half of, now we've got 2 times 1 squared minus 1. That's just 1. And then this one was 7 before, so if we multiply it by 2, that's 14. This one was 17 before, so if we multiply that by 2, that's 34. And then this one was, I don't remember what that one was. 4 squared is 16 times 2 is 32 minus 1 is 33. And so that one's just going to be, 32. So 32 minus 1 is going to be 31. And if we add all of those together and then divide by 2, if we add all those together, we get, looks like 80. And 80 divided by 2 is 40. And because this function is concave up, a trapezoidal approximation is going to be an overestimate. And that's it for that first problem. So we're going to use that same process on our second problem, just a right, a left, a midpoint, and a trapezoidal approximation. A little bit more annoying function this time. Negative 1/2 x squared plus x plus 4. We're going to go from 0 to 4 with 4 subintervals, right? And so 0 to 4 with 4 subintervals, that's going to be 0 to 1, 1 to 2, 2 to 3, and 3 to 4 as our 4 different subintervals. So we'll start with our left approximation, right? And our left approximation, well, it'll just be the length of each of them, which is 1. So I'm not going to write the 1s out this time. Maybe I probably should. I'll write the 1s out because the length of each subinterval is 1. And then when we plug in the left endpoint of the first subinterval, that's 0. So that's 0 plus 0 plus 4. And then we'll do 1 times when we plug in 1, the left endpoint of the second interval, that's negative 1/2 plus 1 plus 4. And then 1 times when we plug in 2, that's negative 1/2 times 2 squared. Well, 2 squared is 4. Negative 1/2 of 4 is going to be negative 2. So we have negative 2 plus 2 plus 4. Then the last one will be when we plug in 3. Right? If we plug in 3 to that, the last subinterval, that 3 squared is 9. So that'll be negative 9/2 plus 3 plus 4. And we'll just figure out what each of those is. So looks like that comes out to be 4 for the first one. Negative 1/2 plus 1 is 1/2. And the 1/2 plus 4 is going to be 9/2. We got negative 2 plus 2 is 0 plus another 4. That's just going to be 4. And then negative 9/2 plus 7 should just be 5/2. And if we add all that together, 9/2 and 5/2 is 14/2, which is 7 plus 4 gives us 15. So our approximation with the left rectangles is 15. And then we can use whether the function is increasing or decreasing on that interval to determine if this is an under or an over estimate. So our derivative, f prime of x, is just going to be negative x plus 1. And so for all of the values between 0 and 4, right, if I take any of those values from 0 to 4 and plug it in, sometimes I get a positive number and sometimes I get a negative number, right? And so on our interval, this is sometimes greater than 0, sometimes less than 0 on this interval from 0 to 4. So for the left and the right approximations for whether it's increasing or decreasing, we can't determine if this is an under or over estimate because it's not strictly increasing or strictly decreasing on our interval. And so if it's strictly increasing or strictly decreasing, you can tell, but if it's not, then you can't figure it out. All right, for our right approximation, we're just going to do this exact same thing, except we're going to use the values at, the right endpoint. So we're going to use the values at 1, 2, 3, and 4, rather than at 0, 1, 2, and 3. So at 1, 2, and 3, we should be getting these exact same things that we got before, right? The value at 1 was this one, right, which was 9/2. So we're going to have 9/2. And then the value at 2 is this one, that's 4. And then the value at 3 was this one, that's 5/2, right? So we got 5/2. And then we have to do the value at 4. Well, the value at 4 is going to be 1 times 4 squared is 16. And 16 times negative 1/2 is negative 8. And then plus the 4. And then plus another 4, which actually ends up just being 0 there, right? And so when I combine all of these together, 9/2 plus 5/2 is again 7. And then we add 4 to that, we just get 11. And for this one, again, we can't determine if it's an under or an overestimate because the function is not strictly increasing or strictly decreasing on our interval. All right, for our midpoint approximation, now for our midpoint approximation, let's see, we had our function, we were doing 0 to 4, it was negative 1/2 x squared plus x plus 4, I believe. Yeah, and so we're taking the midpoints from 0 to 1, 1 to 2, 2 to 3, and 3 to 4, which are 1/2, 3/2, 5/2, and 7/2. So, and all of these are being multiplied by 1 again. So it's 1 times the value at 1/2. Well, 1/2 squared is 1/4, right? And then 1/4 times negative 1/2 is negative 1/8. So we have negative 1/8 plus 1/2 plus 4. And then we're going to have 1 times, when we plug in 3/2, that's going to be 9/4 times the negative 1/2, which will be negative 9/8. So we have negative 9/8 and then plus x, which is 3 halves, plus 4, and then we're going to have 1 times what we get when we plug in 5 halves, which is going to be 25 fourths times the negative 1 half, so negative 25 eighths, plus the 5 halves, plus the 4. And then the last one here is going to be 1 times what we get when we plug in 7 halves. That'd be 49 fourths times the negative 1 half, which would be negative 49 eighths, plus the 7 halves, plus the 4. All right, and so then we'll just do the arithmetic on all of that. Let's see, we got negative 1/8 and negative 9/8. That's negative 10/8, negative 35/8, and then that should be negative 84/8. If we add the negative 4, so negative 84/8. We're going to have a 1 half, a 3 halves, a 5 halves, and a 7 halves. So if we add all those, that's 4 halves plus 12 halves. 4 and 12 is 16. That's 16 halves. That's 8. And then we're going to add together 4 fours, which is 16. Negative 84/8 is the same as negative 42 fourths, or negative 21 halves. So this is negative 21 halves plus 24, which would be 48 halves, which gives us 27 halves. And to determine if this is an under or an overestimate, we're going to use a second derivative. So we already had that f prime was negative x plus 1, so f double prime is just negative 1. That's less than 0, which means that this is concave down. Right? And if the function is concave down on the entire interval, then the midpoint approximation is going to be an overestimate. That one's an overestimate. All right, and for our trapezoidal approximation, we're just going to use our formula, right? B minus A over N divided by 2, and then times our first y value. So when we plugged in 0 to that, we just got 4. And then when we plugged in, it'll be 2 times what we got when we plugged in 1 to that. And when we, what did we get when we plugged in 1 to that? When we plugged in 1 to that, we got 9 halves. So 2 times 9 halves. And then when we plugged in 2 to that previously, right, we ended up with 4. So this is 2 times 4. And then when we plugged in 3 to that, we ended up getting, I believe it was 5 halves. Yep. So 2 times 5 halves. And then when we plug in 4 to that, we don't multiply it by 2. We just put what we get when we plugged in 4. Well, when we plugged in 4 to that, it was 16 times negative 1 half, which was negative 8, plus 4, which was just 0. And so now we end up with 1 half out in front of 4 plus 9 is 13, plus 8 is 21, plus 5 is 26. So we have half of 26, which is 13. And this time it's concave up, which means that, concave down, which means that a trapezoidal approximation is going to be an underestimate, right? And the midpoint in the trapezoidal will always be the opposite of each other. All right, we got a couple more of these to do here. So for this next one, again, same exact process. We're doing negative 4 to 0 this time with n equal to 4. So that's going to be negative 4 to negative 3, negative 3 to negative 2, negative 2 to negative 1, and negative 1 to 0. And so we'll go through and we will write out our left approximation. So our left approximation is going to look like, they're all length of 1. So it's 1 times negative 4 cubed, which is negative 64, and then minus 4 plus 8, Then it'll be 1 times what we get when we plug in -3, which is -27 minus 3 plus 8. And then 1 times what we get when we plug in -2, which will be -8 minus 2 plus 8. And then 1 times what we get when we plug in -1, which is -1 minus 1 plus 8. And if we add all of that together, let's see here. Looks like that first one is -60. So we'll put -60 plus, or actually it's going to be a minus here because that's still a negative. So -60. And then minus, that's 22, -22, so plus a -22. And then that next one is just going to be a -2. And then that last one is going to be +6, which in the end ends up giving us -78. And so then we'll take a look at our first derivative here. F prime is equal to 3x squared plus 1. Well, 3x squared plus 1 is most definitely always positive, which means that this function is increasing. And if a function is increasing, then a left approximation is always going to be an underestimate. So -78 is an underestimate. For our second one, for our right approximation here, we're just going to do 1 times the right endpoint. So at -3, well, at -3, that was this value right here, -22. And then we'll add to that 1 times the value at -2. Well, the value at -2 was -2. And then the value at -1 was 6. Right, and then we need 1 times the value at 0. Well, this value at 0 is just going to be 8. And so if I add all of these together, -22 minus 2 is -24, plus 6 and plus 8 is plus 14. So -24 plus 14 is -10. And because this function is increasing, a right approximation, right, is going to go over the true values of our function, and this will be an over estimate of that integral. So now we'll do the midpoints. So we're going to have to use the values at -7 halves, -5 halves, -3 halves, and -1 half. So again, we have the integral from -4 of x cubed plus x plus 8. And for our midpoint approximation, we're going to have 1 times the value at -7 halves. So that's -7 halves cubed, which is -343 over 8. And then -7 halves plus 8. And then we're going to have 1 times the value at -5 halves. -5 halves cubed is -125 minus 5 halves plus 8. And then 1 times the value at -3 halves. -3 halves cubed is going to be -27 minus the 3 halves plus 8. And then lastly, 1 times the value at -1 half, which is going to just be -1/8 minus a half plus 8. And now we'll just go through and combine all of those things together. And let's see here. We've got 4 8s, right? We've got an 8, an 8, an 8, and an 8. That's going to be 32. We've got a -7 halves and a -5 halves. That's -12 halves. -12 halves minus 3 more halves is -15 halves and -16 halves. So that's going to be a -8 plus our 32. And then we've got -343 eighths. What do we got? Plus or minus 125 eighths minus 27 eighths minus 1/8. If you put all those together, that should be negative 496 eighths. Well, negative 496 eighths is negative 62. So we have negative 62 minus 8 plus 32, which looks like that comes out to be negative 70 plus 32, which is negative 38. And so then we have to determine if this is concave up or concave down to determine if this is an under or an over estimate. So we already had our first derivative, right? F prime was just 3x squared plus 1, and f double prime then is 6x. Well, on this interval, that's always less than 0, right? On negative 4 to 0, which means that this function is concave down. And when a function is concave down, the midpoint approximation is going to be an overestimate. And that'll be the opposite for our trapezoidal one, which we're about to do. Our trapezoidal one ought to be b minus a. So that's going to be 0 minus negative 4 over n, 4 subintervals, all divided by 2. And then we have our trapezoidal formula just says the first y value, so the y when we plugged in negative 4. And when we plugged in negative 4, I don't remember what we got there. It was, if we plug in negative 4 to that, it's negative 64 minus 4 is negative 68, plus 8, that's negative 60. And then we're going to have 2 times what we get when we plug in negative 3. So when we plug in negative 3, that's negative 27 minus 3 is negative 30, plus 8 is negative 22. And 2 times what we get when we plug in negative 2, which is negative 8 minus 2 plus 8, which is just going to be negative 2. And then 1, I'm sorry, we still have a 2 there. We're going to plug in our negative 1. Negative 1 minus 1 is negative 2, plus 8 is 6, so 2 times 6, and then plus just 1 times what we get when we plug in 0, which is 8. And so we end up with 1/2 of negative 60 minus 44, which is negative 104, and then negative 108. If we add 12 to negative 108, that's going to be negative 96, and if we add 8 to that, that's going to be negative 88, and when we multiply that by 1/2, we get negative 44. And again, because the function is concave down, this one is going to be an underestimate, and because a trapezoidal approximation will always underestimate when a function is concave down. All right, so this is our last one of these left, right, midpoint, and trapezoidal approximation problems. These ones are kind of time consuming here. We got 1 over x squared from 1 to 3 with 4 subintervals. So if we have 4 subintervals from 1 to 3, right, 3 minus 1 over 4, that's 1/2. So each one is going to be a length of 1/2, which means we're going to go from 1 to 1/2. I'm sorry, 1 to 3/2. We're going to go from 3/2 to 2. We're going to go from 2 to 5/2. And we're going to go from 5/2 to 3. So those are what our 4 subintervals are going to look like here. And when we do our left approximation, we're just going to do the length of the subinterval, which is 1/2 this time, times the value at each of the left endpoints. Well, 1 over 1 squared is just 1. And then for the next one, we're going to have 1/2 of what we get when we plug in 3/2 into that. Well, 3/2 squared is 9/4, and 1 over 9/4 is going to be 4/9. So we have 1/2 of 4/9. Then we're going to have 1/2 of what we get when we plug in 2, our next left endpoint. Well, that's just going to be 1/2 of 1/4. And then we're going to have 1/2 of what we get when we plug in 5/2. Well, 5/2 squared is 25/4, and if we do 1 over 25/4, that's going to be 4 over 25. And so this ends up being 1/2 plus looks like that becomes 2/9. So 1/2 plus 2/9 plus 1/8 plus 2/25. And I'm not going to bother to do all the arithmetic there. It comes out to be 1,669 over 1,800. And we'll take our derivative, right? The derivative of this is the derivative of x to the negative 2. Well, that's negative 2, x to the negative 3, or negative 2 over x cubed, which on the interval from 1 to 3 is always going to be less than 0. Which means we know that this function is decreasing. And if we have a function that is decreasing, then a left approximation is going to be an overestimate. And for our right approximation, we're just going to do the exact same thing, except we're going to do it with each of the right endpoints. And these all have a width of 1/2 again. So it's going to be 1/2 of the first right endpoint, which was at 3/2. That's this value right here. So 1/2 of 4/9 plus 1/2 of 1/4. That was the next one that we got right when we plugged in 2. And then 1/2 of 4/25. That's what we got here when we plugged in 5/2. And then when we plug in our last right endpoint of 3, it's 1/2 of 1 over 3 squared, or 1/2 of 1/9. So what we end up with is 2/9 plus 1/8 plus 2/25 plus 1/18. And again, I'm not going to belabor the arithmetic here. That ends up being 869 over 1,800. Which this time that's going to be an underestimate because our function is decreasing. And on a decreasing interval, right endpoints are going to always fall underneath the curve. All right, for our next one, it's midpoints. So our function, we were talking about 1 to 3 of 1 over x squared. And our intervals were from 1 to 3/2, from 3/2 to 2, from 2 to 5/2, and from 5/2 to 3. So our midpoints of each of those, right, midway between 1 and 3/2 is going to be 1 and 1/4, right? That's going to be 5/4. This next one here is going to be 7/4, 9/4, and 11/4. So those are what we need to plug in to our 1 over x squared. And so for our midpoint approximation, we're going to have 1/2, because each of the widths is still 1/2, of 1 over 5/4 squared. Well, 5/4 squared is 25/16. So if I flip that, because of the 1 over, it's 16/25. Then we have 1/2 of 7/4 squared. Well, that's 49 over 16, so that'll be 16/49. And the next one will be 1/2 of 16 over 81. And then the last one will be 1/2 of 16 over 121. And of course, those all become 8/25, 8/49, 8/81, and 8 over 121. The arithmetic there is really quite unpleasant. I wouldn't make you do this without a calculator, even though, of course, you should be able to. It comes out to be this. 7,781,792 over, what is that? 12,006,225. And we already had our f prime, right? Our f prime was negative 2x to the negative 3. So f double prime is going to be 6 x to the negative 4, or 6 over x to the 4th, which we know that's always going to be positive no matter what, which means that this function is going to be concave up. And if the function is concave up, then of course we should be getting an underestimate for our midpoint. This value is an underestimate of the true value. And then lastly here, we'll do our trapezoidal rule. So we're going to have b minus a, 3 minus 1 over n, divided by 2, and then times the value at our first y value, which was 1 over 1 squared, so that's 1. And then our next y value there is going to be 3 halves. So this will be plus the value at 3 halves. Or sorry, 2 times the value at 3 halves. And the value at 3 halves was, we squared 3 halves to get 9/4 and took the reciprocal. So it's 2 times 4/9. And then we're going to have 2 times the value at 2, which was 1/4. And then we're going to have 2 times the value at 5 halves. The value at 5 halves was 4 over 25. And then we're going to have the last one will just be 1 times the value at 3, which is 1/9. So 1 plus 8/9 plus 1/2 plus 8/25 plus 1/9. And then multiplied by this ends up being 1/4 out in the front. Again, I'm not going to go through all the arithmetic on that. It becomes 141 over 200. And because the function is concave up, the trapezoids will be an overestimate this time. And that's it for the right, left, midpoint, and trapezoidal approximations. So we'll move on to the next problem type. So for this one, we're asked for us to evaluate the derivative of an integral of a function, right, on some interval, -3 to x in this case. So we're going to use the first part of the fundamental theorem of calculus here, which is what tells us that the derivative of an integral is really just the original function. So since we don't really know the antiderivative of that function inside t squared times 1 plus e to the t, and even if we did, we could still do this. We're just going to let f, capital F, be an antiderivative of that function, t squared times 1 plus e to the t. Which means that what this is now just a derivative of, well, the integral of that function is now capital F, and we evaluate at the upper limit, and we evaluate it at the lower limit, and now we'll take the derivative. Well, the derivative of capital F is just the function in terms of x, so that'll be x squared times 1 plus e to the x, and then capital F of -3, right, this right here, this is just a constant, and so its derivative is just equal to 0. So really what we've got is just x squared times 1 plus e to the x minus 0, or just x squared times 1 plus e to the x. Our next one here is going to be the same basic process. We're just going to let capital F be an antiderivative of that function, the cosine of t cubed. And so now we're just looking at a derivative with respect to x of capital F of the upper limit minus capital F of the lower limit. Well, the derivative of capital F of x is just the function evaluated at x, and then the derivative of a constant, right, the derivative of that constant is just 0, just like in the last one. And so we just have cosine of x cubed minus 0, which is, of course, just cosine of x cubed. For our next one here, we've got two options. One is to just do it exactly the same as we've been doing the other ones. So just to let capital F be an antiderivative of e to the negative t squared. In fact, both ways are going to have us do this. And one option here is going to be, well, just do the exact same thing. This is now the derivative with respect to x of capital F of 7 minus capital F of x. Well, the derivative of this constant, right, that's just a constant, so its derivative is 0. We're just left with the opposite of the derivative of capital F, which is just e to the negative t squared, and then we evaluate it at x. So it's just negative e to the negative x squared. The other option is we can use the rule that says you can flip the limits of integration of something if you make it negative. So this is now just the integral from 7 to x of e to the negative t squared dt, which just ends up being the same thing. It's the derivative with respect to x of the opposite of capital F of x minus capital F of 7. Oops, that's not a 7. And now, of course, this is still a constant, so its derivative is 0. And we just end up with negative derivative of capital F, which is just negative e to the negative x squared. Same process here for this one. We're just going to do the capital F is an antiderivative of t minus 3 over t minus 6. And so we end up with a derivative of capital F of 3x squared minus capital F of 5. Now, this is a little bit different, right? Because once again, capital F of 5, that's just a constant, so its derivative is 0. But when we take the derivative of capital F of 3x squared, that's capital F prime of 3x squared, and then times the derivative of 3x squared, right? That's the chain rule. So we're going to end up with 6x times the derivative of this capital F, which is just t minus 3 over t minus 6, evaluated at 3x squared. So we'll end up with 6x times 3x squared minus 3 over 3x squared minus 6. And that'll be our final answer. Our next one here, again, is going to be pretty much the exact same thing. So we'll say the capital F is an antiderivative of t minus 4 over sine of t. And so we just have a derivative with respect to x of capital F of sine x minus capital F of 4. And again, the capital F of 4, right, that's just a constant. And so its derivative is 0. And we want the derivative of capital F of sine x. Well, that'll be capital F prime of sine x times the derivative of sine x using the chain rule there. It'll be cosine x times capital F prime of sine x, which is just going to be the cosine of x times our original function, t minus 4 over sine t, except we'll replace all the t's with sine of x. So it'll be sine of x minus 4 over the sine of the sine of x. And our next one here, same process again. Capital F is going to be an antiderivative of t plus tangent t. So we just end up with a derivative with respect to x of capital F at x squared minus 1 minus capital F at 3x. Now this time we don't have a constant in there. We have two different functions, so we're going to have two different chain rule pieces here. We're going to have 2x, the derivative of the x squared minus 1, times capital F prime of x squared minus 1. And then minus 3, the derivative of 3x, times capital F prime of 3x, which will just end up being 2x, and then times, well, it'll be x squared minus 1 plus the tangent of x squared minus 1, and then minus 3 times 3x plus the tangent of 3x. And if you want to do some distributing there, you can, but I don't really see any real reason to. So that's going to be our final answer. And this is going to be our last one of these first part of the fundamental theorem of calculus problems. We're just going to let capital F be an antiderivative of t minus 3 over t plus e to the t. And so we're going to have the derivative of capital F at tangent x minus capital F at sine x. And then our derivative then is going to be f prime of tangent, and then times the derivative of tangent, which is secant squared, and then minus the derivative of sine, which is cosine, times capital F prime of sine. So now we'll just go in and replace the t's in our original function with tangent and with sine, and just multiply all of this together. So we end up with secant squared x times, this time we're going to put in tangent, so tangent x minus 3 over tangent x plus e to the tangent x, and then minus cosine x times sine x minus 3 over sine x plus e to the sine x. And that should be our final answer there. All right, our next type of problem here is going to be the ones where we write out these integrals as limits using limits and summations using Newton's notation. So what we need to remember for each and every one of these is that first off, it always starts out as a limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k times delta x. That's what we get as a limit in a summation if we use a right rectangular approximation with an infinite number of rectangles underneath it. Right? And we should also know, as we proved in class, that delta x is always b minus a over n. And also that x sub k is always equal to a plus k times delta x. Okay? So in this case, delta x is going to be 3 minus 0 over n, or just 3 over n. And x sub k is going to be our a value, which is our lower limit, 0. So 0 plus, well, I don't need to write the plus, 0 plus k times 3 over n, or just 3k over n. So we'll just rewrite this as a limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k. So that's just our function evaluated at x sub k, or 3k over n. So 3k over n squared plus 5 times 3k over n minus 1, all times delta x, which is just 3 over n. So that should be our first one here. Our next one, same idea here. Our delta x is just going to be 1 minus 0 over n, since our limits are 0 and 1, or 1 over n. And our x sub k is just going to be 0, our lower limit again, plus k times delta x, or so that's just k over n. And so it should be a limit as n approaches infinity, once again, of the sum from k equals 1 to n of f of x sub k. So that's going to be, well, our function evaluated at x sub k is going to be k over n squared plus the sine of k over n. And then we have to multiply that all by 1 over n, right, by our delta x. And that should be it for that one. That is, make that part of our box here. Our next one here, same idea. Once again, we're just doing x plus 8 this time. So we're going to start off with finding our delta x. Our delta x will be 2 minus 1 over n, which is just 1 over n. But this time our x sub k is going to be a, 1, plus k times delta x. So 1 plus k over n. Since our lower limit isn't 0, we don't just have a single term there for x sub k. It's got something else attached to it this time. So we'll write this out as a limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k, which will be 1 plus k over n, plus 8, all times our delta x, which is 1 over n. And it would probably be nice if we rewrote this out as a limit as n approaches infinity of the sum from k equals 1 to n of 9 plus k over n times 1 over n. That will be our final answer there. Same idea here for this one. We're going to find delta x first. That'll be b minus a over n, or 3 over n. And our x sub k will be a plus k delta x. So this time our a is 2, that lower limit, plus k times delta x of 3k over n. And so we'll just put this into the limit and the summation that we know we need to use. The limit as n approaches infinity of the sum from k equals 1 to n of our function evaluated at x sub k. So that will be 2 plus 3k over n squared minus 3 times 2 plus 3k over n. And then, of course, we're going to multiply all of that by delta x. So that's just all multiplied by 3 over n. And that should be our final answer there. And this is our last one of these limit summation problems. So same idea though. Delta x is going to be b minus a over n, or 3 over n. And x sub k will be our lower limit of 1 plus k times that delta x. So k times 3 over n is just 3k over n. Then we'll go over here and we'll write out our limit. It's a limit as n approaches infinity of the sum from k equals 1 to n of our function at x sub k. So that'll be e to the 1 plus 3k over n plus the tangent of 1 plus 3k over n. All times our delta x, which is just 3 over n. And that is the last of those limit summation problems. Next up, we're going to look at these problems where we have some known integral values of functions, and we're going to evaluate some other integrals that involve those functions. So we want the integral from 1 to 3 of 3f of x minus 4h of x. Well, really what that is it's 3 times the integral from 1 to 3 of f of x dx minus 4 times the integral from 1 to 3 of h of x dx. Well, 3 is just 3, and the integral from 1 to 3 of f is 4. So we'll start off with 3 times 4, and then we'll subtract from that 4 times the integral from 1 to 3 of h, which is negative 6. So we've got 12 plus 24, which is just 36. For our next one here, this one's actually really straightforward. We don't need any of the known integrals up there. The integral from 2 to 2 of any function, or the integral from a to a, right, if these upper and lower limits are the same, is always just equal to 0. Okay? Because if there's no interval, we can't have an area underneath that curve, right? So the area is just going to be 0. These next couple here are using the same known integral values. So now we want the integral from 1 to 7 of h of x. Well, you can see up here that I have 1 to 3 and 3 to 7 of h. And so this integral should be the same as the integral from 1 to 3 of h plus the integral from 3 to 7 of h. Because I'm taking the area from 1 to 3 and adding it to the area from 3 to 7. That should give me the total area from 1 to 7. So from 1 to 3, h is negative 6. From 3 to 7, h is 10. We'll just add negative 6 and 10 together to get 4. And for our next one, we want the integral from 1 to 5 of f of x. Well, we have 1 to 3 of f of x, and we have 5 to 3 of f of x. If we could have the integral from 3 to 5 of f of x, then we could add the part from 1 to 3 to the part from 3 to 5, and that would give us the whole thing from 1 to 5, right? This would be the same as the integral from 1 to 3 of f plus the integral from 3 to 5 of f. Now we've got the integral from 1 to 3. That's just 4. But we don't have 3 to 5, we have 5 to 3. Well, we can flip the limits of integration and make it negative. So we can say minus the integral from 5 to 3 of f of x dx, which is going to give us 4 minus this negative 2. And 4 minus negative 2 is just 6. And for these last two here, again, the same known integral values. So we want the integral from 3 to 6 of 5 times h of x. Well, first of all, that's just 5 times the integral from 3 to 6 of h. Pull that 5 out. Now, if I wanted the integral from 3 to 6, but I had the integral from 3 to 7, I'd have to subtract an integral from 6 to 7 from that, right? Because if I had everything from 3 to 7 and I subtracted just the piece from 6 to 7, that'd leave me with the piece from 3 to 6. Well, I almost have the piece from 6 to 7 because I have the opposite of it. I have the integral from 7 to 6. So first, let's write this as 5 times the integral from 3 to 7 of h minus the integral from 6 to 7 of h, which we don't have. But we do have the first piece of it. So now we have 5 times the integral from 3 to 7 of h is 10. And then we're going to, we're actually going to flip that limit of integration, right, to make it 7 to 6, because we do have that one. And when we do that, we turn it into a plus sign here because it was already a minus sign. So we're going to say plus the integral from 7 to 6 of h, which now is 5 times 10 plus 5. And 10 plus 5 is 15, and 5 times 15 is 75. All right, for our next one here, we're looking at the integral from 3 to 1 of h. Well, I have 1 to 3 of h, so just flip the limits of integration. It's the opposite of the integral from 1 to 3 of h, which is the opposite of negative 6, which is, of course, just 6. All right, for our next one here, we got a new set of integral values. And we're starting off with the easiest one here. From 1 to 1, there's no interval. Therefore, the integral must be 0. Then we've got the integral from 1 to 7 of 3 times f of x dx. Well, first we'll pull the 3 out. All right, so this is 3 times the integral from 1 to 7 of f. Well, I don't have the integral from 1 to 7 of f. But I do have the piece from 1 to 4 and the piece from 7 to 4. So if I had 1 to 4 and 4 to 7, that would work out really well. So let's write that. 1 to 4 plus 4 to 7. And now we'll say 3 times. The part from 1 to 4 is just 1. And then since we don't have 4 to 7, but we have 7 to 4, we could flip the limits of integration. So it's minus the integral from 7 to 4 of f of x, which is going to give us 3 times 1 minus that negative 2, which is the value from 7 to 4. And of course, that becomes 3 times 3, which is 9. All right, for our next one here, we want 1 to 5 of 4f of x plus 1 to 5 of 3h of x. Well, I have 1 to 4. I'm sorry, 1 to 5 is what we need. I have 1 to 5 of f, and I have 1 to 5 of h. So just pull those constants out. It's 4 times the integral from 1 to 5 of f plus 3 times the integral from 1 to 5 of h. And so then we've got 4 times 1 to 5 of f is 3, and 3 times 1 to 5 of h, which is 10. So it looks like we've got 12 plus 30, which is 42. Our next one here is the integral from 1 to 7 of h. Well, we've got 1 to 5 of h, and if we also had 5 to 7 of h, that could be the whole part from 1 to 7. But we don't have 5 to 7, we have 7 to 5. So we'll rewrite this first as an integral from 1 to 5 of h plus an integral from 5 to 7 of h, recognizing that we have 1 to 5 of h, that's 10. but we'll have to subtract the opposite integral from 7 to 5 of h. And that gives us 10 minus our negative 5, which is 10 plus 5, which is just 15. All right, we got a couple more of these here. So same integrals again. We're going from 4 to 5 now of f. So if I just wanted the piece from 4 to 5, and I had the piece from 1 to 5, I could take off the piece from 1 to 4, and that would give me only the part from 4 to 5, right? So the integral from 1 to 5 of f minus the integral from 1 to 4 of f ought to give us only what's left from 4 to 5, which is what we're looking for. So from 1 to 5, it's 3. We'll subtract the part from 1 to 4, which is 1. Well, 3 minus 1 is 2. And for our last one here, we're looking at the integral from 4 to 1 of f. Well, we can just flip the limits of integration and make it negative. It's the opposite of the integral from 1 to 4 of f, which is going to be the opposite of 1. So just negative 1. All right, now we're looking for the average value of this function. So the mean value theorem for integrals says that the average value of a function is just 1 over b minus a times the integral from a to b of f of x dx. So we'll just do 1 over 2 minus negative 1 times the integral from negative 1 to 2 of our function. Well, 1 over 2 minus negative 1 is just 1/3. So we have 1/3 of the integral there, which is x cubed over 3 plus 3x, just using the power rule on both of those. And we'll plug in negative 1 and 2. So we end up with 1/3 of 2 cubed is 8, so 8/3 plus 6 minus, and then negative 1 cubed is negative 1, so negative 1/3 minus 3. The 8/3 minus a negative 1/3 is going to be 9/3, so that's 3, plus 6 is 9, and then minus another negative 3 ought to be 12, so 12 over 3, 12 times 1/3, is just going to be 4. All right, for our next one here, we're looking for the average value of 3x squared minus 2x minus 1 from 0 to 4. So we'll use that same formula, 1 over b minus a times the integral from a to b of our function, 3x squared minus 2x minus 1. So we have 1/4 of x cubed minus x squared minus x, all done with the power rule, from 0 to 4. So we end up with 1/4 of 4 cubed, which is 64, minus 4 squared, which is 16, minus 4. And then when I plug in 0 to x cubed, x squared, and x, those are all zeros. So this is just minus 0 at the end. Well, we have 1/4 of, if we do 64 minus 20, that's 44. So 1/4 of 44 is 11. All right, we're looking for the average value of the sine function on the interval from 0 to 2 pi over 3. So that'll be 1 over 2 pi over 3 minus 0 times the integral from 0 to 2 pi over 3 of sine of x. Well, 2 pi over 3 minus 0 is 2 pi over 3. And if you do 1 over that, that's 3 over 2 pi. So we have 3 over 2 pi. And then we have the integral of sine, which is negative cosine, evaluated from 0 to 2 pi over 3. So that's 3 over 2 pi. And then it's negative cosine of 2 pi over 3 minus the negative cosine of 0. Now, I want to caution people here as we evaluate this. A lot of the time, when you see a lower limit of 0, people just say, oh, I'm going to ignore that because the lower limit's 0, so the function's 0. Well, that's not the case here, right? The cosine of 0 is not 0. In our previous problem, right, x cubed, x squared, and x were all equal to 0, so we could kind of just ignore that. But here, that's not the case, right? The cosine of 0 is not 0, so don't just get rid of that second term. A lot of people just forget about writing that second term. And so there's a fair number of cases like cosine, or let's say e to the x, where when you plug in 0, you don't get 0. So just be careful about that. So now we have 3 over 2 pi times the negative cosine of 2 pi over 3. Well, the cosine of 2 pi over 3, that's in the second quadrant, so it's negative, and it's negative 1/2. So we have negative 1/2, which will just be positive 1/2. And then we've got the negative cosine of 0, which will be plus 1. So we have 3/2 times 3 over 2 pi, which is 9 over 4 pi. All right, a couple more of these mean value theorem problems. So we have tangent 2x. So we're going to do 1 over pi over 6 minus 0 times the integral from 0 to pi over 6 of the tangent of 2x dx. Now we have an integral for tangent x, or tangent u, but we'll do the u substitution for this. U is going to be 2x, so du is 2 dx. So what I'm going to do is I'm going to throw in a 2 inside of here and a 1/2 outside of here to cancel out. And I can rewrite this integral. So we have, first of all, pi over 6 minus 0 right here, right? It's just pi over 6. And if I take the reciprocal of that, that's 6 over pi. And if I multiply 6 over pi by 1/2, I get 3 over pi. So it's 3 over pi times the integral of now tangent u du, right? Because the tangent 2x becomes tangent u, and the 2 dx becomes du. And when x is 0, u is 0. So this lower limit's going to stay as 0. But when x is pi over 6, our upper limit, u will be twice that, which will be pi over 3. Okay, so now we have 3 over pi times the integral from 0 to pi over 3 of tangent u du. And we should know that the integral of tangent is negative natural log absolute value cosine of u. If you don't remember that that's the integral of it, you can always rewrite it as sine over cosine and do the u substitution on it. But we proved that in class, so it'd be useful if you just memorize the integral of tangent as negative natural log of cosine, or negative natural log of absolute value of cosine. So now we'll just plug in our values. Right? We're going to go from 0 to pi over 3. No need to put it back in terms of x because we converted everything to terms of u. So we've got 3 over pi times negative natural log of the cosine of pi over 3. Well, the cosine of pi over 3 is just 1/2. So this is negative natural log of 1/2. And then minus our negative natural log of the cosine of 0. Well, the cosine of 0 is 1. And so now we should be able to simplify this all down really nicely. The natural log of 1 is 0, so all of that just goes to 0. And the negative natural log of 1/2, well, if you bring this in as an exponent, right, that becomes 1/2 to the negative 1, which is just 2. So really that's 3 over pi times the natural log of 2, or 3 natural log of 2 over pi. All right, here we're looking for the average value of x root x squared minus 3 on the interval from root 3 to 2. So we'll start off with 1 over b minus a, so 2 minus root 3, times the integral from root 3 to 2 of x root x squared minus 3 dx. In order to find this integral, we're going to have to do a u substitution, where u is going to equal the stuff inside that square root, x squared minus 3. And du will be 2x dx. So we'll throw our 2 out here, which means we're going to multiply this by 1/2 now. And we'll see that when x is root 3, u just becomes root 3 squared, which is 3 minus 3. So we just get 0, right? We plug in root 3 in here. And if we plug in 2 in there, when x is 2, we just get u is equal to 2 squared, or 4 minus 3. We just get 1. So this ends up being 1/2 of 1 over 2 minus root 3 times the integral from 0 to 1 of u to the 1/2, right? The 2x dx becomes the du, and the root u is just u to the 1/2. So we end up, once again, with 1 over 2 times 1 over 2 minus root 3. Now our integral is going to be 2/3 of u to the 3/2 evaluated from 0 to 1. Well, the 1/2 and the 2/3 should multiply together to make 1/3. So we've now got 1/3 of 1 over 2 minus root 3. And then 2/3, really we can rewrite this like this, right? The 2/3 is being multiplied by the u to the 3/2, so I can pull that off the side, which is why I turned the 2/3 and the 1/2 into a 1/3. And then u to the 3/2 is just 1, and 0 to the 3/2 is 0. And so we just end up with 1/3 of 1 over 2 minus root 3. And if you want to distribute the 1/3 through, you're welcome to, but this is also completely fine. So for this one, we're just looking at a regular indefinite integral. We're just going to use a power rule on it. So the integral of x squared is just going to be x cubed over 3. We'll go up to power of 3 and divide by 3. And then for minus 3x, go up to a power of 2 and divide by 2. So minus 3/2 x squared. And then the 8 just becomes plus 8x. And of course, don't forget your constant at the end. Our next one here is, again, just going to be a power rule integral. So 3x to the 4th will go up to 3x to the 5th, and then we'll divide by 5. So 3/5 x to the 5th, and then a minus 5/3 x cubed. The x goes up to x squared, and we'll divide by 2, and the minus 1 becomes minus x. And of course, don't forget your plus c. This one, whenever we have a function in the numerator that can easily be divided, each term can easily be divided by the singular term in the denominator, that's always going to be our first step here. So we'll rewrite the integral as 5x squared over the cube root of x, right? So that's an x squared over an x to the 1/3, or x to the 6/3 over x to the 1/3. So that'll be 5x to the 5/3. And then 2x is x to the 1st over x to the 1/3, so that'll be minus 2x to the 2/3, and then 1 over x to the 1 over the cube root of x will just be x to the negative 1/3. So this will be our new integral, right? We're just going to integrate this. So 5/3 will go up to 8/3. So we'll have x to the 8/3, and when I divide by 8/3, that's the same as multiplying by 3/8. So 5 times 3/8 will be 15/8. And then minus 2x to the 2/3, that'll go up to x to the 5/3. And of course, we'll divide by 5/3 or multiply that 2 by 3/5. So that'll be 6/5 x to the 5/3. X to the negative 1/3 goes up to x to the 2/3. And we divide by 2/3, which would be multiplying by 3/2. And of course, don't forget your constant. We'll use our same process as the last one here. On this one, we'll just divide everything by x to the 1/2. So 7x cubed divided by x to the 1/2 should be 7x to the 5/2. So we'll do that before we integrate. The 8x to the 1/2 over x to the 1/2 will just be plus 8. And then a minus x squared over x to the 1/2 will be a minus x to the 3/2. And now we'll just integrate all of those using the power rule. This goes up to x to the 7/2, and we'll divide by 7/2 or multiply by 2/7. Well, 7 times 2/7 is just 2, so that's 2x to the 7/2. The 8 just becomes plus 8x, and our minus x to the 3/2 will go up to the 5/2 and divide by 5/2, so multiply by 2/5 minus 2/5 x to the 5/2, and of course, don't forget your constant. For our next one here, we've got two options. One option is to do a u substitution, and the other option is just to recognize that this is the same as an integral of root 6 times root x dx, and just pull the root 6, the constant, out in front. So I think that's what I'll do here. So we now have root 6 times the integral of x to the 1/2 dx. Well, that's just root 6 times x to the 3/2. We divide by 3/2, or we multiply by 2/3, plus some constant. And then we can just distribute that root 6 in. We end up with 2 root 6 over 3 x to the 3/2 plus some constant. And again, root 6 times this constant is just some other constant. That's why I use c sub 1. And here I just used c at the end. All right, for our next one here, we have the integral of x cubed times the square root of x squared minus 8. And so we'll start off by doing a u substitution by what's inside the square root. So we'll let u equal x squared minus 8, which means that du is 2x dx. Well, I don't have a 2x in there, but I could put a 2 in there if I put a 1/2 out in front. And x cubed is just x times x squared. So I put the 1/2 outside, the 2 inside, that cancels, and I've broken the x cubed down into x times x squared. And then I still have my square root of x squared minus 8 dx. And so from there, now we can do all of the substitutions, except that I need to know what x squared is equal to, right? Well, x squared, using this, x squared is equal to u plus 8. So I can replace the x squared with u plus 8, and everything else should simplify down nicely. So we've got the 2x dx becomes my du, my x squared is my u plus 8, and the root x squared minus 8 just becomes root u, or u to the 1/2. This u to the 1/2 can be distributed to both of these terms so that we can just use the power rule to integrate. So this is 1/2 the integral of u to the 3/2 plus 8u to the 1/2 du. And so now we'll integrate. We've got 1/2. U to the 3/2 will become 2/5 u to the 5/2 using the power rule. And then 8u to the 1/2 will go up to 3/2, right? So we're going to have plus, and it's going to be u to the 3/2. When we divide by 3/2, we multiply by 2/3. So that's plus a 16/3 u to the 3/2 plus some constant. And when we distribute the 1/2 in, we'll end up with 1/5 of, not u to the 5/2, but x squared minus 8 to the 5/2. We always want to go back to our original variable with these indefinite integrals. And then 16/3 times 1/2 will be 8/3, and it'll be x squared minus 8 to the 3/2 plus some constant. All right, for our next one here, we're just going to use the same idea. We're going to let u equal x squared plus 1, and then du will be 2x dx. And I've already got a x in there. I've got a 10x. Well, 10 is just 5 times 2. So I'll pull the 5 out and say this is 5 times the integral of 2x root x squared plus 1 dx. And this will just become 5 times the integral of u to the 1/2 du. The 2x dx will become the du, and root x squared plus 1 is just u to the 1/2. So now we'll integrate. We'll have 5 times 2/3 u to the 3/2 plus some constant. And when we multiply the 5 in, we'll end up with 10/3 of our u, which was x squared plus 1 to the 3/2. Always make sure you write that back in terms of x, and then plus some constant. All right, for our next one here, we just have the square root of 4x plus 7. So we're going to let u equals 4x plus 7, and du will be 4 dx. So we'll just put a 1/4 outside so that we can put a 4 on the inside. The 1/4 and the 4 canceling each other out, allowing us to rewrite this as 1/4 of the integral of just u to the 1/2, right? Because root u would be u to the 1/2, and the 4 dx becomes du. So the integral of u to the 1/2 is, once again, 2/3 u to the 3/2 plus some constant. We'll distribute the 1/4 through. 1/4 times 2/3 is just going to be 1/6. So we end up with 1/6 of 4x plus 7 to the 3/2 plus some constant. All right, our next one here is the integral of tangent of 3x. Now we have a rule for the integral of tangent. The integral of tangent is negative natural log absolute value of the cosine, and we proved that in class. If you don't remember how to get that, or if you forget it during the test or something, you can always rewrite tangent as sine over cosine and do the u substitution for cosine to find that. But I'm going to work under the premise that we actually memorize the rules that I've asked you to memorize. So we'll just do the u sub on the 3x. So if u is 3x, then du is just 3 dx, meaning I can throw a 1/3 outside and a 3 on the inside here, and turn this into 1/3 of the integral of tangent of u du, right? The 3 dx becomes the du, just like we have here, and tangent 3x becomes tangent u. And since we know that the integral of tangent is negative natural log absolute value cosine of u plus some constant, we can now just distribute that 1/3 through and turn the u back into 3x, giving us negative 1/3 the natural log of the absolute value of the cosine of 3x plus some constant. For this cotangent one, we're going to use the same process, except now it's the integral of cotangent that we need to know. Right? So the integral of cotangent is natural log of the absolute value of sine. We proved that one in class also. But if you forget on the test what the integral of cotangent is, just rewrite it as cosine over sine and do a u sub for sine. So we're just going to do a u sub for the 8x, letting du be 8 dx. So we'll put a 1/8 out in front with an 8 on the inside. And now we'll rewrite it in terms of u. 1/8 the integral of cotangent u du, right, where the 8 and the dx turn into the du, and cotangent 8x just becomes cotangent u. So this is 1/8 of the natural log of the absolute value of the sine of u plus some constant, which is just 1/8 the natural log of the absolute value of the sine of 8x plus some constant. All right, for our next one here, we have cosine of x over sine to the 4th of x. Well, what we want to notice here is that one piece of this, the piece that has the sine in it, if I take the derivative of sine, I get cosine. Right, so I could just do a u substitution for sine of x, because that lets me have du be cosine x dx, and then I'm just in terms of one function when I turn it into terms of u. Right, so this just becomes an integral of du over u to the 4th power. Right, or we could just rewrite this as the integral of u to the negative 4th du, which when we integrate just becomes u to the negative 3 over negative 3 plus some constant. I don't really need the 1 on it this time. I don't have anything out in front. So now this is really just negative 1 over 3 u cubed, which is sine cubed x, plus our constant. For cosine to the 5th of theta, our technique for these is to always just try to get it into two different trig functions. So I want to turn it into, where we have an odd power here, we want to just always break it down into the cosine to the 4th of theta and a cosine of theta d theta. Because anytime I have an even power of cosine, right, or of sine, I can rewrite it using some trig identities. right? So cosine of the fourth would be the same as cosine squared squared. And we know that cosine squared is 1 minus sine squared of theta. So really, what I've got here is the integral of 1 minus sine squared theta squared times cosine theta d theta. And then we'll just do a u substitution where u is equal to the sine of theta, because du will just be the cosine of theta d theta, which I have. So this just becomes an integral of 1 minus u squared squared du. Well, 1 minus u squared squared, we should be able to just distribute that out. That's 1 minus 2u squared plus u to the fourth du, which gives us u minus 2/3 u cubed plus u to the fifth over 5 plus a constant. And from there, we can just turn all the u's back into sine of theta. And we have sine theta minus 2/3 sine cubed theta plus sine to the fifth theta over 5 plus a constant. And that should be our final answer. So for this next one, we're just going to use the same idea. This time it's sine to the seventh. So we'll just rewrite it as sine to the sixth x times sine x. And then that's the same as 1 minus cosine squared x. Right, that's just the sine squared x cubed, right? So I'm going to cube that. I probably should have written that step in there, but right, that's sine squared of x cubed is the same as sine to the sixth, and sine squared of x is just 1 minus cosine squared of x. And so we have 1 minus cosine squared x cubed. And we can then just do a u substitution here. We're going to let u equal cosine x, and du will be negative sine of x. Well, I don't have negative sine x. So what I will need to do is I'll have to rewrite this as the opposite of the integral of the opposite of 1 minus cosine squared x cubed times sine x dx, so that I do have the negative sine x dx to cancel out. So now we end up with the opposite of the integral of 1 minus u squared cubed du. And we should be able to distribute out 1 minus u squared cubed using like the coefficients, 1, 3, 3, 1 from Pascal's triangle. So this is now the opposite of the integral, and that'll become 1 minus, because it's an a minus b cubed. So it's 1 minus 3 times our u squared, and then it'll be plus 3 times u to the fourth, and then it'll be minus u to the sixth du. So now this is the opposite of u, and then minus 3u squared will just become minus u cubed, so minus u cubed, and then plus 3/5 u to the fifth, and then minus u to the seventh over 7 plus some constant. I'll rewrite everything back in terms of u, and I'll distribute the negative through. So we have negative cosine x, because u was cosine, plus cosine cubed x, minus 3/5 cosine to the fifth x, plus cosine to the seventh x over 7, and then plus some constant. So again, when we have that odd power there on the sine or the cosine, that's a nice little trick there to turn it into two different trig functions so we can use that u sub. All right, for this one we have sine squared x times cosine cubed of x. Well, we've already got two trig functions, but they're both being raised to power. So what we want to do is we want to get one of them down to a singular power, and then the rest of it all in terms of the other trig function. So the easiest way to do that is going to look at this as sine squared x times cosine squared x times cosine x dx, because that'll allow me to turn the cosine squared x into 1 minus sine squared x. So we'll have sine squared x times 1 minus sine squared x times cosine x dx. And when I do that, we can now do the u substitution where u is sine of x and du is cosine of x dx. So I can replace the cosine x dx with du and all the sines with u. So this just becomes an integral of u squared times 1 minus u squared du. And the integral of u squared times 1 minus u squared is the same as the integral of u squared minus u to the 4th du, which is just u cubed over 3 minus u to the 5th over 5 plus some constant. We'll just replace all the u's with sine, giving us sine cubed x over 3 minus sine to the 5th of x over 5 plus a constant. All right, for O here, this next one, sine of x over cosine to the 6th of x, we're just going to notice that the derivative of cosine is negative sine. So we almost have a nice easy u substitution where we could just make u cosine. In fact, that's what we're going to do. We're going to let u equal cosine x, where du is negative sine x dx. And we'll just need to put a negative outside and a negative inside that integral. That'll turn this into the opposite of the integral of du over u to the 6th, or the opposite of the integral of u to the negative 6th du. And when I integrate u to the negative 6th, we got that opposite out in front, the integral of u to the negative 6 should go up to u to the negative 5, and we'll divide by negative 5, plus some constant. And when I distribute that negative sign through and turn everything back into terms of x, the negatives will cancel. So we're just going to have 1 over 5 cosine to the 5th of x plus some constant. All right, for our next one here, we have the integral of x minus 3 over x squared minus 6x plus 1, which would be really nice if we could substitute out that denominator. And so if we think about doing that, if u was x squared minus 6x plus 1, then du would need to be 2x minus 6 dx. Well, I don't have a 2x minus 6. All I have up there is an x minus 3. But we might note that if I multiplied x minus 3 by 2, we would have 2x minus 6 dx. So I can do that as long as I put a 1/2 out in the front of my integral. So we're going to say this is 1/2 of the integral of 2x minus 6 dx, which is du, over u. And this is an integral that we should know. This just gives us 1/2 of the natural log of the absolute value of u plus a constant. We'll go back into terms of x, so this is 1/2 of the natural log of the absolute value of x squared minus 6x plus 1 plus some constant. We'll do a similar thing here. We're going to let u equal x squared minus 4x minus 1. So du would just be 2x minus 4. Well, I don't have 2x minus 4, I have 4x minus 8. But 4x minus 8 is the same as 2 times 2x minus 4. So really what I've got is the integral of 2 times 2x minus 4 over x squared minus 4x minus 1 dx. And I can then just pull the 2 that's inside out if you want to. And then rewrite this as du over u. So our integral is just 2 times the natural log of the absolute value of u plus a constant, which is 2 natural log absolute value of x squared minus 4x minus 1 plus a constant. For our next one here, similar idea. This time we have x squared plus 2x plus 5 cubed in the denominator, but that doesn't really affect our ability to make that same substitution that we've done in the past. if u is x squared plus 2x plus 5, then du would be 2x plus 2. And if I have 2x plus 2, well, I'd have to multiply the x plus 1 by 2, which would mean I'd have to multiply by 1/2 out in front. So we'd end up with 1/2 of the integral of du over u cubed. Well, that's fine, because we know how to integrate u cubed. It doesn't have to just be a u down there. So we'll say this is 1/2 of the integral of u to the negative 3 du, or 1/2 of u to the negative 2 over negative 2 plus a constant, using the power rule. And then, of course, we can distribute the 1/2 through, which is going to give us a negative 1 over 4 times u squared, which was x squared plus 2x plus 5. And then we'll add to that some constant. For our next one here, we're going to use just, again, that same kind of process. We're going to let u equal the thing that's being raised to the 5th power in our denominator, so x squared plus 8x plus 1. So du is 2x plus 8, which means we're going to have to multiply that x plus 4 by 2 to turn it into 2x plus 8, which means we're going to have to multiply by a 1/2 out in the front. So we've got 1/2 of the integral of du over u to the 5th, or 1/2 of the integral of u to the negative 5 du. Well, u to the negative 5 will go up to become u to the negative 4, and we'll divide by negative 4 plus some constant. We'll distribute the 1/2 in to give us negative 1 over 8. And then our u to the 4th in the denominator will become x squared plus 8x plus 1 to the 4th plus some constant. For our next one here, x squared plus 5x plus 1 over x minus 2. This is one of the ones where we want to just divide that numerator by the binomial that we have in the denominator. And I think the quickest way to do it is synthetic division. Since 2 makes x minus 2 equals 0, we'll put a 2 up there in the box and put a coefficient of 1 for the 1x squared, a 5 for the 5x, and a 1 for the plus 1. We'll just use synthetic division real quick to integrate this. Bring down the 1. Multiply the 1 by the 2 that's in the box, gives us a 2. Add the 5 and the 2 to give us 7. Multiply the 7 by the 2 to give us 14. And add those together to make 15. This becomes an integral of just 1x plus 7 plus 15 over my original x minus 2 denominator. And so now we're just going to integrate each piece of this. The x becomes x squared over 2. The 7 becomes 7x. And the 15 over x minus 2 has to be done with a u substitution, but it's a u substitution just for that singular piece of it, right? And if u is x minus 2, like if we just think about just this piece of it as its own separate integral, if u is x minus 2, then du is just dx. So really we just have 15 over u that we're integrating. Well, 15 over u is 15 natural log absolute value u, or in this case, 15 natural log absolute value of x minus 2. And of course, plus our constant. So anytime we just have that x minus a term in there, where it's just an x, not like 2x or 3x in that denominator, the u sub becomes very simple, and we can just kind of treat it like there's not really a u sub going on, even though in the background there is. All right, we'll use the same process here on this one. Since negative 2 is what makes x plus 2 equal to 0, put a negative 2 in the box. We have 1x cubed. Don't forget the 0x squared, the negative x, and the minus 7 for our synthetic division. Bring down the 1. 1 times the negative 2 in the box is negative 2. Add 0 to negative 2, you get negative 2. The negative 2 is multiplied, make 4. Negative 1 and 4 is 3. 3 times the negative 2 in the box is negative 6. And negative 7 and negative 6 is negative 13. We started at cubed, so we dropped down to squared. So this just becomes 1x squared minus 2x plus 3 using these coefficients here. And then minus 13 over x plus 2 dx. And again, the first three pieces of it are just done with the power rule. X cubed over 3 minus 2x squared over 2, or minus x squared, plus 3x. And then the last piece is a little u sub for x plus 2. Just like with the last one, though, it just becomes minus 13 natural log absolute value x plus 2, plus, of course, our constant. Just be careful about that, though. If this was like a 2x down here, then that u sub doesn't work as simply. You really probably should write it out unless you've gotten good at doing those ones in your head. All right, for our next one here, same idea. We're just going to divide everything by x minus 3. Using synthetic division, we put a 3 in the box. 1x to the fourth, 1x cubed, 5x squared, negative 1x, and positive 1. Bring down the 1. 1 times 3 in the box is 3. The 1 and the 3 added makes 4. 4 times the 3 in the box is 12. 5 and 12 is 17. 17 times the 3 in the box is 51. Negative 1 plus 51 is 50. 50 times the 3 in the box is 150, and add those at the end to get 151. This becomes an integral of x cubed, because we started at x to the fourth and we dropped down to 1x cubed, plus 4x squared plus 17x plus 50, and then plus 151 over our original denominator of x minus 3, which that one will again just become a nice simple u sub at the end, and the rest will just use the power rule. Okay? So this is x to the fourth over 4 plus 4/3 x cubed plus 17 halves x squared plus 50x. And then our simple u sub here on the x minus 3 just gives us 151 natural log absolute value of x minus 3 plus our constant. All right, for this next one, e to the x over 2 plus x squared. The e to the x over 2 part of it, we're going to have to use a u sub for. But the x squared part of it, we don't. So it might be useful for you to write those out as separate integrals. Right? The e to the x over 2 part, we're going to let u equal x over 2, and du will be 1/2 dx. So what I want to do is I want to put in a 1/2 here with a 2 out in front. Right? And so we'll rewrite this as 2 times the integral of e to the u du plus the integral of x squared, which is just x cubed over 3, plus some constant. Well, if we integrate 2 times e to the u, we just get 2 times e to the u plus some constant, plus x cubed over 3 plus that other constant. And of course, well, e to the u was just e to the x over 2. So we have 2e to the x over 2 plus x cubed over 3. And two constants, constant 1 and constant 2 added together, are just some other constant. We'll do the same basic thing here for this one, right? The e to the 7x part, we're going to rewrite that as just e to the 7x dx. I can just integrate x. I'm not going to bother to write it as two separate integrals this time. The integral of x is just x squared over 2. Now for the piece that I'm still integrating here, I want to let u equal 7x, where du is just 7 dx. So I'll put in a 7 with a 1/7, giving me 1/7 the integral of e to the u du plus my x squared over 2 plus that constant. That's just 1/7 of e to the u plus some other constant, plus x squared over 2 plus that first constant. And when I rewrite this, it just becomes 1/7 e to the 7x plus a 7th of constant 2 plus constant 1 plus the x squared over 2. All those constants are just some constant. So we have 1/7 e to the 7x plus x squared over 2 plus the constant. All right, for our next one here, we have x minus 7 to the 6th So we're just going to do a basic u sub here. We're going to let u equal x minus 7, and du will just be dx. So really this just becomes an integral of u to the 6th du, which would be u to the 7th over 7 plus a constant. And then we'll just rewrite it in terms of x. So x minus 7 to the 7th over 7 plus that constant. This is a similar problem as the last one, but it becomes a little bit more difficult because we have 3x minus 4 to the 4th, right? It's 3x instead of just x. So we still want to do the same thing where u is 3x minus 4, and du then becomes 3 dx, which means we're going to have to put a 3 on the inside of that integral, along with a 1/3 on the outside of that integral. So we've got 1/3 of the integral of u to the 4th du now, which is just 1/3 of u to the 5th over 5 plus some constant, which becomes 1/15 of u, 3x minus 4, to the 5th, plus some constant. All right, here for this one, we have the 4th root of 5x plus 1 in the denominator, right? So it's dx over the 4th root of 5x plus 1. We're still going to use the same idea, where we're going to let u equal 5x plus 1, and du is just going to be 5 dx. So I'm going to want to put in a 5 on the inside and a 1/5 on the outside. Okay? And so now we should be able to rewrite all of this into terms of u. So the 1/5 stays as a 1/5. The 5 dx will become a du. And then the 4th root of 5x plus 1 in the denominator is a 4th root of u in the denominator, or just a u to the negative 1/4. So now it's just a power rule problem. It's 1/5 of, and then we'll integrate u to the 1/4. So we'll go up to u to the 3/4 and divide by 3/4, which is the same as multiplying by 4/3, plus some constant. And we'll rewrite this, 4/3 times 1/5 is just going to be 4/15. And then we've got u to the 3/4, so 5x plus 1 to the 3/4 plus some constant. All right, for our next one here, we're just going to do the same thing. Again, we're going to substitute out that x squared minus 1 that's inside the cube root in the denominator, but this time it becomes du is 2x dx, which is perfect because we've already got 2x dx in that integral. So we'll just have an integral of, well, the cube root of u in the denominator is u to the negative 1/3, and then we have du. So we'll just integrate u to the negative 1/3 du. Well, the integral of u to the negative 1/3 should go up to u to the 2/3, and then we multiply by the reciprocal of that, 3/2, plus some constant. And then we'll just replace the u with x squared minus 1. So we have 3/2 of x squared minus 1 to the 2/3 plus a constant. All right, just a couple more of these indefinite integrals, and then we'll finish up with a few definite integrals. We have 7 over the square root of x minus 4. So really that's just, if u is x minus 4, then du is dx. This is really just the integral of 7u to the negative 1/2, right? Because a root x minus 4 in the denominator is just like x minus 4 to the negative 1/2, so it'll be u to the negative 1/2. And we'll go from that, we'll go to 7u to the 1/2, and we'll divide by 1/2, which is the same as multiplying by 2, plus our constant, which just gives us 14 root u, or 14 root x minus 4, plus our constant. All right, and here is our last indefinite integral for this problem set. So we have 2 over the cube root of 5x plus 6. We'll do u equals 5x plus 6. so that du is 5 dx. So if du is 5 dx, then we need to put a 5 in there. Now, if you don't mind dealing with like the annoying fractions and stuff, you can just kind of say, well, if I multiply the 2 by 5 halves, right, that's going to turn that into a 5 dx, which would mean I have to put a 2/5 out in the front to cancel out that 5 halves. So we're going to have 2/5 of the integral of u to the negative 1/3, because it's a cube root of u in the denominator. And then 2 times 5 halves is 5, so the 5 dx becomes the du. Then we'll just integrate using the power rule. It's 2/5 of u to the 2/3 divided by 2/3, which would be times 3 halves, plus some constant. Distribute the 2/5 into that, so you'll end up just getting 3/5 then. 2/5 times 3 halves will be 3/5. And then our u is 5x plus 6 to the 2/3, and of course plus some constant. So that's it for the indefinite integrals. We'll finish up with a few definite integrals, starting off with a nice easy one here, where all we have to do is just use the power rule. X squared's integral is x cubed over 3, and then minus x squared over 2, and then minus x. And we'll evaluate from 1 to 4. So 4 cubed is 64, so this is 64/3, minus 4 squared is 16, 16 over 2 is 8, so minus 8 minus 4, and then minus 1/3 minus 1/2 minus 1. And if we just combine all of that together, at 64/3 minus 1/3 is 63/3. 63/3 is just 21. So we have 21 minus 8 minus 4, so minus 12. And then minus a negative 1 will be plus a 1, and then minus a negative 1/2 will be plus a 1/2. Well, looks like that's, what does that come out to be? 21 minus, or ends up being 22 minus 12, which is 10. 10 plus a 1/2 would be 10.5, or 21 over 2. All right, our next one here is just an integral of tangent x dx. So we know that the integral of tangent is just negative natural log absolute value of cosine of x. We're going to evaluate that from 0 to pi over 4. And again, I think I mentioned this earlier, but be careful when you are looking at a lower limit of 0, because that doesn't necessarily mean that the thing inside there becomes 0. So let's write this out. It's negative natural log of the cosine of pi over 4 minus negative natural log of the cosine of 0. Well, the cosine of pi over 4 is root 2 over 2, so this is negative natural log root 2 over 2. And then plus the natural log of the cosine of 0. Well, turns out actually the cosine of 0 is 1, but the natural log of 1 is 0, so this term is 0. So we just have negative natural log of root 2 over 2. If you want to, I think it'd be nice to rewrite this a little bit. That's the same as if I pull the negative inside as an exponent, that just becomes natural log of 2 over root 2. Well, 2 over root 2 is just root 2, so this could be rewritten as just the natural log of root 2. If you want, 1/2 the natural log of 2 is also fine. And any of these really are fine answers and could be expected on a multiple choice question on the AP test. I like these two the best though. All right, if we're going to integrate sine of 3x from 0 to pi over 6, we're going to first have to start off with a u substitution. So we're going to have to let u equal 3x, and du will be 3 dx. So we'll put a 1/3 out in front, and then we'll put a 3 on the inside. And then that'll let us write this as 1/3 of the integral of sine of u du. And when x is 0, u will also be 0. And so we can leave that lower limit as the same. But when x is pi over, I wrote pi over 3 over here, but that was pi over 6. And when x is pi over 6, u is going to be 3 times pi over 6, which is pi over 2. So this becomes 1/3 of the integral from 0 to pi over 2 of sine of u du. The integral of sine, as we should know, is negative cosine. So we've got 1/3 of negative cosine u from 0 to pi over 2. Well, that's 1/3 of the negative cosine of pi over 2. The cosine of pi over 2 is 0. So that's just 0. And then minus the negative cosine of 0. Well, the cosine of 0 is 1. So negative 1 is just 1. So we end up with 1/3 of 1, which is just 1/3. For our next one here, we have the integral of x times root x squared plus 1 from 0 to root 3. Anytime we see something like this, we want to always start off trying to do a u sub for what's inside the root. That gives us du is 2x dx, which we can see that we can put a 1/2 outside and a 2 on the inside to allow us to rewrite this integral all in terms of u. So before we do that, though, we need to convert our limits. So when x is 0, u is going to be 0 squared plus 1, so 1. And when x is root 3, u is going to be root 3 squared, which is 3, plus 1, so it would be 4. So this now becomes 1/2 of the integral from 1 to 4 of u to the 1/2 du. So we'll just integrate. 1/2. The integral of u to the 1/2 should be u to the 3/2 and then times the reciprocal of 3/2, so 2/3. And we'll evaluate that from 1 to 4. Now, the 1/2 and the 2/3, those can be combined together to just give us 1/3. So we end up with 1/3 of 4 to the 3/2 minus 1 to the 3/2. Well, 4 to the 3/2 is square root of 4 is 2, and cube it is 8. So we have 8 there. And then minus the 1 to the 3/2. 1 to the 3/2 is just 1. So we end up with 7/3. All right, our next one here, the integral from 0 to 5 of e to the 2x minus x squared plus x. Now, the e to the 2x part requires a u substitution, but the minus x squared and the plus x parts do not. So I can treat this like two separate integrals. So let's do that. This is an integral from 0 to 5 of e to the 2x dx, and then plus, we can just integrate the negative x squared into negative x cubed over 3, and the x into x squared over 2, evaluated from 0 to 5. All right, so I've already done the last two pieces of it, and I'll need to do something here with this. Well, if I want to deal with this, I'm going to let u equal 2x, and du will be 2 dx. So we end up with a 2 on the inside and a 1/2 on the outside. So now it'll be 1/2 the integral of e to the u du. But when x is 0, u is also 0, so my lower limit stays as 0. But when x is 5, u is 2 times that. It's 2x, so that'll be 10. And then we'll add to that this whole thing, which we can start evaluating right now if we want. Right? This is plus negative 125 thirds plus 25 halves, and then minus 0, because I plug in 0 to x cubed over 3 and x squared over 2. They're both equal to 0. Now we'll just do our integral here. So this is 1/2 of e to the u from 0 to 10. And then we will add to that this negative 125 thirds plus 25 halves. Let's see. I don't know. I'm not gonna deal with that yet. 125 thirds plus 25 halves. We'll figure that out in a second. This is now 1/2 e to the 10th minus 1/2 e to the 0, so minus just 1/2. And then we still have the minus 125 thirds and the plus 25 halves, which is going to give us 1/2 e to the 10th. And then negative 1/2 plus 25 halves is 24 halves. That's 12, right? And so 12 is 36 thirds. So I have a negative 125 plus 36. That should be a negative 89 thirds. So minus 89 over 3. And that should be our final answer here. Now we just got 3 more here to go. The integral from 0 to 2 of x squared minus x minus 1 over x minus 3. So this one will be another one where we just want to use synthetic division. We'll put the 3 in the box because that's what makes x minus 3 0. 1x squared, negative 1x, and negative 1 over here. Bring down the 1. Multiply by the 3 in the box. Add in the same column to give us 2. Multiply by the 3 in the box and add again. Giving us now an integral of x plus 2 plus 5 over x minus 3 dx, right? We started at x squared, so these drop down to x, the constant, and then the term divided by the remainder divided by our original denominator. So now we'll just integrate, giving us x squared over 2 plus 2x, and then we've done a few of these already. The 5 over x minus 3 is just 5 natural log absolute value x minus 3. We're going to evaluate all of that from 0 to 2. And of course, you can see this is why it's important that we have the absolute value on that inside the natural log, because otherwise we'd be getting with something that was undefined here. So we end up with 2 squared over 2. That's 4 over 2, so 2. And then plus 2 times 2, so 2 plus 4, plus 5 natural log of the absolute value of 2 minus 3, that's negative 1. And then minus, if I put in 0, it's 0 plus 0 plus 5 natural log absolute value negative 3. Well, 2 and 4 is 6. The absolute value of negative 1 is 1, and the natural log of 1 is 0, so this term goes away to 0. So we just end up with 6 minus 5 natural log of the absolute value of negative 3, which is just 3. So 6 minus 5 ln 3. All right, our second to last one here. Nice, easy one, actually. We're just going to integrate this using the power rule, right? This is x to the 1/4. So this will go up to x to the 5/4, and we'll multiply by 4/5. And we'll just evaluate that from 1 to 16. So 4/5 times 16 to the 5/4 minus 1 to the 5/4. 16 to the 5/4. If you 4th root 16, you just get 2. And then if you raise 2 to the 5th power, you get 32. And then 1 to any power is just 1. So we have 4/5 of 31. Well, 4 times 31 is 124. So our final answer there is 124 over 5. All right, and our last one here is an integral of cosine cubed x from pi over 6 to pi over 3. So similarly to the indefinite integral ones that we did like this, we want to rewrite this as an integral from pi over 6 to pi over 3 of cosine squared x times cosine x, so that I can then rewrite to an integral of pi over 6 to pi over 3 of 1 minus sine squared x using a trig identity times cosine x dx. And so when we do that, that allows us to do the u substitution where u is equal to sine of x and du is cosine of x dx. So now this integral just becomes an integral of 1 minus u squared du, right? The cosine x dx turns into the du, and the sine squared becomes u squared, so it's just 1 minus u squared. We do have to change our limits of integration, so if x is pi over 6, then u is the sine of pi over 6. Sine of pi over 6 is 1/2. And if x is pi over 3, then u is the sine of pi over 3, which is root 3 over 2. So now we'll just integrate, giving us u minus u cubed over 3 from 1/2 to root 3 over 2. So we'll just go through the arithmetic here, root 3 over 2, and then we'll cube root 3 over 2, right? It's 1/3 of that. So if we cube root 3, that's 3 root 3. And if we cube 2, that's just 8. And then we'll subtract from that what we get if we put in a half, which will be 1/2, minus 1/2 cubed is 1/8, times 1/3 is 1 over 24. And if we combine our like terms here and like get some common denominators and all that fun junk, looks like we're going to have the 1/2 minus a 1/24, right? So that's going to be 11/24. So we're going to be subtracting 11/24 at the end. And then we've got root 3 over 2, and we've got 3 root 3 over 24. So I'm going to have to combine, well, I can cancel out these 3's first of all, right? Those will cancel. And so really, if I just multiply this by 4 and 4, I'm going to have 4 root 3 over 8 minus 1 root 3 over 8, which will just be 3 root 3 over 8. So we have 3 root 3 over 8 minus 11/24. So if you want to get a common denominator for the whole thing, you're welcome to, right? You get 9 root 3 minus 11 all over 24. But this answer is perfectly acceptable. And that is the end of this walkthrough for the integrals test review.